with the second day of our course, and we are going to start right now. I hope you enjoy we hope that you enjoy the first day. And today we will go more in detail on our main scientific interest, the study of the ionosphere. So I will give the word to Claudio to start the first part of the lesson today. Enjoy the course.
Good morning, good afternoon, good everything to everybody. I would like to start this session today with a Q&A session. So I don't know if some of you has some questions about the last lesson. Maybe you had the time to digest a bit what we said last time. So please, if you have some doubt or questions or curiosity, you can write on the chat, and Lucilla will be there to answer to your questions. And so don't be shy, and let's go for an interactive lesson that is more fun. So last time we have seen something about the space weather in general. We learned that all the stuff related to space weather starts from the sun. So we recalled some basic concepts about the sun morphology, the solar wind, the interplanetary magnetic field, and the interaction of the solar wind and the IMF with the Earth magnetosphere. At the end, we saw as well the definition of some geomagnetic indices useful to study the impact of the solar wind, of a solar storm, on the geomagnetic field. So today, we are going more in detail on the ionosphere. That is the main topic of these lessons. So we move from the outer space to the ionosphere. That is, as you probably already know, the upper atmosphere, the part of the atmosphere in which the presence of ions and free electrons is able to interfere, to impact to the propagation of the electromagnetic wave from in the range of the kilohertz to the gigahertz. So the ionosphere is that part of the atmosphere that stands from let's say 50 kilometers up to 1,000 kilometers and above. And as we will see during this lesson today, this ionosphere is a very complex medium in which the electromagnetic wave can propagate, feeling different effects and impact from the ionosphere itself. The ionosphere in general is a very low density plasma, which plasma we mean a gas or a medium in which you have the presence of free charge, so ions and electron, but the ionosphere is a very low density plasma. So the density and concentration of the free electrons is very low with respect to the neutral density. So only a very small part of the atmosphere is actually ionized. The ionospheric plasma has some peculiar characteristics and parameters that can define the morphology of the plasma. That is called critical frequency, and this critical frequency is related to the opportunity of the free electrons to be excited by an electromagnetic wave passing through the ionosphere. So as you can see from the image here, the ionosphere show a very large variability with the altitude, but also with the day and night variation. How the ionosphere is formed. Again, all the ionosphere is there because of the sun. So we have the neutral atmosphere surrounding the Earth, and we have the sun radiation coming from the sun. So if we want to consider the equation, the continuity equation that is able to describe the variation of the electron density in the ionosphere with respect to time, we have to consider three main sources and terms in the equations, that are the production term, that is indicated here with Q, the loss term, that is L, and the part related to the transport of the plasma. So the plasma is not only created and destroyed, as we will see, by the sun radiation and the recombination, but is also transport from one region to another one. So in the balance, we have to consider, to describe the variation of the electron density, we have to consider the transport terms as well. How the production term is ruled. I mean, the process that mainly create free ions in the ionosphere, free electrons in the ionosphere and ions in the ionosphere, is the so-called photoionization. The photoionization is the process in which a photon coming from the sun is able to put away an electron from a neutral atom or molecule, and so at the end we will have an ion, a positive ion, and a free electron produced by the interaction between the sun radiation and the neutral atoms and molecule. So if you can see here, we have a neutral atom indicated with A. Sun radiation is coming, a photon is interacting with the atom, and then at the end we have an ion and a free electron. So with this kind of process, we are able to produce a plasma starting from the neutral atmosphere. And just to give you an idea, the radiation that is able to do it is the very high energetic radiation from the sun. So let's say from the UV to upper frequency on the electromagnetic spectrum. So here we can see an example of this reaction of this photoionization, in which we have an oxygen atom that is interacting with a photon with a particular frequency and wavelength that is able to interact with the oxygen atom and to create the O+ ion plus the electron. So if we consider a neutral atmosphere that is composed by one neutral, so we can consider the atmosphere as composed by only oxygen in this case. We can see we are talking about the Chapman theory. So the Chapman theory is the theory that describes the behavior of the electron density in the ionosphere if we consider a monochromatic radiation coming from the sun and an atmosphere that is composed by only one neutral, in this case oxygen. So from the sketch below, you can see that the combination of the energy coming from the sun with the H, in which H is the altitude with respect to the Earth's surface. We have the energy coming from the sun that is decreasing when we move from the top of the atmosphere down to the Earth's surface, because the energy is absorbed passing through the atmosphere. And the distribution of the neutrals with the altitude, that is here basically represented as a monotone behavior decreasing with the altitude, we can obtain a layer like the one you can see on the right plot that describe the ionospheric layer as a with an electron density that show a peak in the electron density that we will see in a while, is located at about 300 kilometers, 400 kilometers, something like this. So if we consider the Chapman theory, so only one neutral, or only one frequency on the sun radiation and the distribution of the neutral atmosphere, we can obtain what we call the Chapman layer, alpha layer. So a distribution that show only one peak in the distribution of the electron density. And let's say that this is not far from the reality. I mean, Chapman, with this very simple theory, was able to represent the ionosphere quite well. But okay, let's imagine to have this atmosphere composed by the oxygen and the electromagnetic wave. So if we do some simple calculation, we can obtain a peak on the electron density that is of the order of 10 to the 7 electron per centimeter cube. But this kind of electron density was never measured in the ionosphere. So what happened? Is the Chapman theory not, useful in the Earth ionosphere? Okay, so something is clearly happening to these ion and electrons in order to maintain the electron density below the one calculated by the simple Chapman theory. And the answer stands in the chemistry of the ionosphere and atmosphere. So basically, we have two processes that is able to let the electron density decrease. That's the plasma recombination and the neutral plasma processes. So, summarizing, the processes that is able to modify the distribution of the free electrons in the ionosphere are the photoionization, that is the process that is able to create free electron in the atmosphere, and we have two main processes that are the photoionization and the recombination. The recombination is the mechanism by which an electron is able to recombine with an ion. So this is a loss process that is able to let the electron density decrease. So we have these two processes that is one against another, the photoionization that is creating electrons, and the recombination and attachment as well, that is able to recombine electron and ion. So, and then the other process that is able to influence the distribution of the electron density is, as we have seen on the very first slide, is the transport effect. These processes results in a different distribution of the electron density on the ionosphere with respect to the simple Chapman layer. And this distribution was in the first slide. Let me go back here. As you can see on the left. Okay. On the left, you have a typical day-side ionosphere in which you can recognize different layer that is called D layer, E layer, F1 and F2 layer. And a typical, and on the right side, a typical night side ionosphere in which you can recognize, okay, forgot for a moment this sporadic E, in which you can recognize basically only one layer that is called F layer. So these layers are different regions of the ionosphere, showing different characteristics and created by different processes. So in each layer, you have a predominant process that is able to depict the morphology of that layer. So let's start with the very first layer, so the one closest to the Earth's surface. This is the F layer. Here you can see that the altitude of, the D layer that is included between 60 and 90 kilometers of altitude. This is not, I mean, altitude so sharp. The altitude can vary a lot, but more or less you have this range of altitude. This layer is the one that is able to completely absorb radio frequency in the HF region with a frequency, let's say, less than 3 megahertz. So the HF electromagnetic wave are more or less absorbed by the D layer, and this have an implication on the ionospheric measurement, as we will see in a while. Mainly, the D layer is can be considered as a Chapman layer ruled by the production due to the Lyman alpha radiation from the sun. In the D layer, you have the more heavy atoms of the atmosphere and molecule of the atmosphere that is basically nitric oxygen, and these layers tend to disappear when the sun radiation disappears. So during the night, during the very first moment of the night, the D layer suddenly disappear because you have due to the high density in this layer, you have a very fast recombination processes. So you have not anymore the sun radiation that is ionizing the atmosphere, so the D layer disappear. The D layer again is the layer that is from the D layer up to 150 kilometers. Again, here we have a very rapid chemistry, so recombination, and as you can see from the sketch here on the left, you have the distribution of the electron density of the E layer with respect to the local time. So this E layer show a peak at noon local time, but rapidly disappear after dusk. So during the night, also the E layer as the F layer disappear very rapidly. And the E layer is the density in the D layer is ruled so by the solar zenith angle basically and the latitude. So as you can see from the right plot, the E layer show a behavior that varies with the latitude. So we have a maximum at the equator and the minimum at the polar region. The F layer. The F layer is the one at the top of the okay, no, not at the top, but is the one up to, let's say, 400 kilometers and above sometimes. And in this F layer, not only the let's say the radiation and the photoionization is important, but also the transport. So in this case, the Chapman theory failed completely, and this layer cannot be described as a Chapman alpha layer. So as you can see here, the behavior with respect to the local time and latitude and season is not so sharp. So again, you have a peak with respect to local time that is slightly shift with respect to the noon local time, and the behavior with the latitude show these two peaks behavior that we are going to explain very well in a while. And also the season is important for the F layer. So as you can see here, you have a more, let's say, a different electron density at the peak of the layer during the summer and during the winter. Since the F layer is ruled by the transport and not only by the photoionization, in this F layer, we cannot recognize a simply variation due to the solar zenith angle. So we can in some way studies what we call some anomalies. Which anomalies here we mean the behavior that is not reproduced by the Chapman theory and the simple photoionization theory. So here I listed some of them. There is the winter anomaly, the annual anomaly, and the semi-annual anomaly. But okay, maybe we can. I leave to you at the end of the lessons. You will have these slides, so you will find here some details about these anomalies. But I don't want to go in detail now because maybe I'm delayed. So we have seen how the ionosphere is forming and how the different electron density is distributed along the vertical. So I don't know if you have some question about this very first introduction to the ionosphere.
No question in the chat? Don't be shy. Okay. Sylvain, are the models that reproduce the shape of the electron density? List some models that reproduce the shape of the electron density.
Sure. As they exist, they are a lot, and they are mainly can be divided the model in two big categories. That are the empirical model that is based on data, so you can process the data in a way that we will see a bit tomorrow, in order to obtain a climatological view of the ionosphere. So you have the empirical data, and you have the physical model that is based on equations and on the first principle of the physics ruling the morphology of the ionosphere. But there are a lot. Yeah.
No other questions.
Okay, so I leave the floor to Lucilla.
So let's go ahead into the general description of the ionosphere, looking at the variability of the ionospheric plasma itself. So with Claudio, we have seen that the variability that are considered as regular variability, so somehow predictable variability. We have seen the day and night changes in the ionosphere with the appearance and disappearance of the layers, the seasonal variability with this so-called winter anomaly, even if the word anomaly is a little bit misleading in this sense, because it's a known anomaly, is not something that is unknown, but is well known now. The latitudinal dependence and the variability due to the cycle of the solar activity that we have seen on Tuesday, when we have seen the changes in the sunspot number that follow a cycle that lasts about 11 years, and in which we have seen that we are now leaving the ascending phase of the current solar cycle. So the number of the sunspots are increasing and increasing, and in this sense also the perturbation coming from the sun, so flares, CMEs, coronal holes are more frequent in this period and will increase further till the peak of the maximum. The perturbed ionosphere is very often hardly to be predicted. And this unpredictable change can be induced by different sources. So you don't have to think that only space weather induced perturbation on the ionosphere, but you see here a list of other possible sources of variability. For instance, the neutral atmosphere variability. This happens, for instance, with the so-called atmospheric gravity waves. These are wave-like mode of the neutral atmosphere that induced in turn also a wave-like mode in the upper atmosphere, so in the ionosphere. Another important source of variability of perturbation from the quiet state of the ionosphere is due to the occurrence of earthquake, volcano, and tsunami events, with the so-called coupling between the lithosphere, atmosphere, and ionosphere. Again, the most visible response of the ionosphere to these events is a wave-like mode, a quasi-periodical movement of the electrons into the ionosphere. Another very important source of variability for the occur in the southern part of Argentina and in the Antarctic Peninsula, and the darkness of the sun due to an eclipse induce, of course, a different chain of processes. In particular, there is a weakening of the photoionization role, and this induces generally lowering of the electron density on the ionosphere, but it's not so straightforward, so simple to understand, and there are several teams all over the world, among them also the one led by Dr. Molina, that try to understand how that eclipse can induce a perturbation on the ionosphere. There are also anthropogenic sources of different kinds. For instance, when a rocket is launched into the ionosphere, we can have some kind of response. Generally, this kind of reaction of the ionosphere are very transient, in the sense that in few time the ionosphere tends to come back to a steady state. Other kind of anthropogenic sources induced by the human beings are the heating that are used, for instance, from ground-based instruments to make experiment into the ionosphere and to try to understand with a controlled experiment at ground how the ionosphere behaves with respect to an heating induced by this kind of equipment. And then last but not least, for us, there are the space weather events. The space weather events that we will see in the following slides, but we have already mentioned. Try to predict, to nowcast, to monitor, to nowcast, to forecast, and possibly to mitigate the effect of space weather events on the technological system, and in particular the chain of space weather events that induce into the ionosphere perturbation such to cause on technological systems some kind of damage, of corruption. So we see just few examples of the variability that I was mentioning. The latitudinal dependence, for instance, this is the first one that we would like to highlight in this course. We have seen on Tuesday the geometry of the geomagnetic field that in a very first approximation can be considered as a dipole field with the double lobe that we have learned that on the sunward side is compressed by the action of the solar wind, while in the anti-sunward side it is elongated in what we call a tail. Anyhow, we have learned that this kind of geometry leaves some weakness on our shielding, on the atmosphere shielding towards the arrival of the solar wind. In the poles of our atmosphere, which from the sketch you see that when a single particle in the sketch of the solar wind is coming from the sun towards the earth, when this particle encounters the geomagnetic field line, it cannot directly penetrate the field line because of the charge of the particle and the existence itself of the geomagnetic field. But this particle is driven by the geomagnetic field into a spiral that drive that particle, and of course all the particles embedded in the solar wind into the polar at the polar latitude of our atmosphere. This is why we have the reaction of the neutral atmosphere to this injection of energy that appears as the auroral emission. So the auroral emission are the reaction of the atmosphere to the entrance of electrons into the upper atmosphere at ionospheric altitude, and are visible at bare eyes because the reaction is visible in the optical wavelength. For what concern the high latitude, again, maybe you remember that on Tuesday we defined the interplanetary magnetic field as the solar magnetic field that can be considered the interplanetary magnetic field because it's the bulk of the magnetic field of our system is due to the presence, to the existence of the solar magnetic field. So we have defined the interplanetary magnetic field according to a certain geometry that see the definition of the reference frame as on the plane of the ecliptic plane, Bx and By, and the Bz direction as the vertical with respect to ecliptic plane. And we have seen that Bz component direction is crucial to understand what will happen when the solar wind is coming towards the Earth. When the Bz, so the interplanetary magnetic field that we have seen is considered embedded, frozen in the solar wind, approach our geomagnetic field, this interplanetary magnetic field can be southward or northward. Southward, in the southward condition, we have the so-called reconnection between the geomagnetic field, so the magnetic field of the Earth, and the interplanetary magnetic field. In this case, the reconnection happened at the day side of the magnetopause, so the part of the magnetosphere that is facing towards the sun. And in this case, we have that the F region, so the highest part of the ionosphere, that region plasma flow anti-sunward over the polar caps. So let's see if I can use the pointer. Okay. So the flowing is coming from this direction. This is noon, so the sun is here, somewhere here. And what you have is that the flow in the F region is anti-sunward, so it's coming from noon to midnight in this direction, and return sunward in the auroral oval. So you see from this sketch here. What you have that was already mentioned by Claudio on Tuesday. A configuration is a configuration of the electric ionospheric potential as a two cells. and the sites of the cells are defined according to the sign of the dy component of the interplanetary magnetic field. The condition in which you have an IMF that is northward, so BZ is positive, is more complex to define and to describe. What you have is that the reconnection happen at the magnetotail, so not in the noon, but at the midnight direction, and the configuration of the electric potential of the ionosphere is more complicated and can be four cells, a four cells configuration, as you are seeing in this first row of the sketch, or in 3 cells. It depends on how intense is, how strong is the northward direction. If it's very strong, you have a 4 cell configurations, while 3 cells is generally describe the electric potential of the ionosphere when the BZ northward is weak. So in a very few words, in a nutshell, the mechanism of the aurora occurrence. Again, this is a recap somehow. You have this pointer, okay? Okay. The magnetic field lines, when the particles come in embedded into the flux of the solar wind, arrive, approach the geomagnetic field, they spiralize towards the poles, and what you have is the direct entrance of electrons, in this case, into the upper atmosphere. In the upper atmosphere, they encounter the atmospheric components. In particular, we care about oxygen and nitrogen. And at different rates, they excite the ions. And the results of this excitation is the emission of the light on optical wavelength in the different color, according to the different components that were hit, according to the different height to which they have been hit. So in this beautiful picture from the International Space Station, you can see the auroral oval shape, which we have an emission, green aurora emission, and you can appreciate the different boundary and the different extension of the auroral oval. Another beautiful picture. This was taken over our station in Antarctica that we share with the French colleagues. This is Concordia station in Don Sea in Antarctica. That is, Concordia is inside the cap. So to go back to this slide, and we have mentioned already this position, the cap is inside the auroral oval. Concordia is inside the auroral oval and can see very peculiar condition of the ionosphere. So let's go back to the low latitude ionosphere. So we have seen that there are latitudinal dependence. We have seen in a nutshell the condition taking place in the polar ionosphere, in the high latitude ionosphere, more correctly. We are now in the low latitudes, at low latitudes, as we are here in Tucumán. And for this part of the ionosphere, we can say that the plasma is characterized by the existence of the so-called equatorial ionospheric anomaly. Again, this is a a little bit misleading definition, because it is now well known, or even if it is still hard to be predicted in details, especially for space weather applications. Anyhow, this is defined as a region located around the magnetic equator at ±20 degrees, but this is a climatological description, so it is an average description of the position of the equatorial anomaly. The characterization is to have a very high electron density concentration at F2 height. In this part of the globe, what you have is that the geomagnetic field lines are almost horizontal to the Earth's surface. So what you have is that the magnetic field lines that you see in this sketch here are almost horizontal to the Earth's surface. And you have also the concurrent process induced by the solar heating and the tidal oscillation in the lower ionosphere. This set a sheet, a zonal electric current in the E region that combine with the horizontal magnetic field result in a E cross B response of the ionosphere that you see. If you think to the electric field into the lower ionosphere with the right hand rule, and you think to the horizontal magnetic field, you have as a result an uplift. The E cross B results is an uplift of the plasma into the F layer. This is concentrated exactly where we seen this higher concentration of the electron density. These two spots here in the sketch. We call these two sketch here, two spots here, the crest of the anomaly, in the sense they are the why this is called in that way. The blue, of course, are the electrons, and the orange lines are the geomagnetic field lines. And you see, like a fountain, how the uplift behave into the ionosphere. We are seeing a while a view from above instead of being and in this way you can perceive how the two crests appear over the globe. I'm playing again just for a while to see again with you. So in this part of the world, the ionosphere is always daily perturbed by the existence during the day of the equatorial anomaly. So this is one of the reasons for which we have a strong collaboration with the University of Tucumán to study the regional ionosphere. So, questions? Okay. Yeah, okay.
Maybe all is clear, or all is unclear.
Unclear, or all
okay.
is very
Does
cloudy.
this anomaly appears all the day?
The anomaly appear during daytime, because the conditions are such that this process that I have just described appear during local daytime, of course.
And another question is, the South Atlantic anomaly generates further anomalies.
Yes, of course, but the Southern Atlantic anomaly is a little bit southern of this anomaly. There are two different anomalies.
Another question is how earthquakes and tsunamis perturbate the ionosphere.
This is a very good question, and this is something that is still matter of debate. For sure, we seen after an earthquake, because there is also a big debate on the ionospheric perturbation as a forerunner, as a precursor of the ionosphere. But let's go to talk just a while about the response of the ionosphere to the quakes. The quakes induce a chain of reaction in the atmosphere. The most evident and maybe the most consolidated, Claudio, we can say that are the acoustic gravity waves induced in the atmosphere. And so they are visible as a wavy-like mode of the ionosphere with certain wavelength that can be recognized according to the position of the epicenter, the distance to the epicenter. And so that is considered, of course, the source of the perturbation.
No other question.
Okay, so I leave the word again to Claudio.
Okay, so now we know, let's say, very well how the ionosphere is formed, how the ionosphere behaves at different latitude, different local time, something about the different season. So now we want to move to describe how we can measure the electron density in the ionosphere. This is the reason why we know all the stuff about the ionosphere, because we are able in some way to measure directly or indirectly the distribution of the electron density in the ionosphere. So basically we can say that almost all the techniques that are used to measure the ionosphere is based on remote sensing. So on the use of an electromagnetic wave passing through the ionosphere. There are other techniques that are in situ measurements that are able to measure directly the ionosphere by a satellite flying into the ionosphere. But basically and historically, we can measure the ionosphere by using electromagnetic wave at different wavelength and frequency as the probe of the ionosphere. So to do that, we have to know how an electromagnetic wave is perturbed when passing through the ionosphere. And as you know very well, the parameter defining the way in which an electromagnetic wave is, let's say, deviate and the velocity change when the electromagnetic wave passes through a medium different to the vacuum is the refractive index. In the case of the ionosphere, the equation defining the refractive index is the one you can see here, that is called Hartree-Appleton equation. You can see here only Appleton, but actually Hartree was the one discovering and defining for the first time this equation, and Appleton was his professor. So the right name is the Hartree-Appleton equation. Here you can see that the refractive index, the square of the refractive index n, is defined by basically three different parameters that are x, y, and z that are related to different aspects of the ionosphere. So the x is expressed by the ratio between the square of the plasma frequency and or angular velocity and the frequency of the wave passing through the ionosphere. So here omega is related to the frequency of the electromagnetic wave ionospheric plasma is characterized by peculiar critical frequency, critical plasma frequency that is here in this X component. Y is related to the presence of the magnetic field. So omega H is the electron zero frequency that is defined by some universal constant, and the intensity of the magnetic field in which the plasma is embedded. And then the Z component, that is the component related to the collision between electrons and ions. So here Ni is the collision frequency of the ion and electrons. So as you can see here from the equation, if we have some important, let's say, characteristic, we magnetic field induce an effect that is able to split an electromagnetic wave passing through the ionosphere and through a medium embedded in a magnetic field into two different components with different polarization, as we can see in few slides by talking about ionograms. So if we have a plasma embedded in a magnetic field, we have this effect that is able to split the electromagnetic wave in two components with two orthogonal polarization. Then if we put the Z component to 0, and this is the case for the ionosphere, I mean, in most of the cases we can neglect the collision between ion and electrons, because we said that the ionospheric plasma is a very low density one. So this collision is the one ruling the absorption of the electromagnetic wave, and in most of the cases for the electromagnetic wave with a frequency higher than few megahertz, we can completely ignore this term. So if we put Z equal to 0 and Y equal to 0, the equation defining the refractive index is this simple one here at the bottom. So the square root of 1 minus x squared. So let's imagine now to have this plasma with no magnetic field, no collision impacting the electromagnetic wave path through the ionosphere. We can define the plasma frequency, this Fp, with this equation here, in which we have the N, that is the electron density, so the density of the free electrons in the ionosphere. Q is the electron charge, and this is the electric constant in the vacuum, and M is the mass of the electron. So basically the plasma frequency can be considered as almost equal to 9 and times the root square of the electron density. So from here you can see that to a given electron density corresponds a given plasma frequency. This is the principle in which the HF sounding of the ionosphere is based. So just to recall what we said a few seconds ago, the refractive index under some assumption can be defined as this one, so root square of 1 minus plasma frequency square over the frequency of the electromagnetic wave square. So this is valid for every altitude, every point of the ionosphere. So by using this principle, as we can see, we can define the critical frequency of the ionosphere that is related to the peaks of the electron density distribution on the ionosphere. Here you have a sketch of an ideal electron density distribution in which we can recognize this critical frequency or critical plasma frequency indicated by the green arrows that is related to the peak of the E region, F1 region, and F2 region. So by exploiting this one-to-one correspondence between plasma frequency and electron density, we can define and we can measure the critical frequency of the ionosphere and then the electron density of the peaks of the ionosphere. By knowing that when we are sending an electromagnetic wave through the ionosphere and the frequency of the electromagnetic wave is equal to the plasma frequency, a reflection of the electromagnetic wave happened. Okay, so when we have that this term Fp squared over F squared is equal to 1, so the refractive index tends to 0, a refraction happened. So this is why one of the most used way to measure the ionosphere, and the very first one from an historical point of view, is the use of HF radio wave, that are the radio waves in the range of let's say few megahertz, from 1 to 20 megahertz. That corresponds to the electron density that is typical of the ionosphere. So this is the wave and the frequency that we are able to send to the ionosphere in order to receive a backscatter electromagnetic wave. So with this range of frequency, we can send an electromagnetic wave when the frequency of the wave will encounter an electron density for which the plasma frequency is equal to the frequency of the wave. We have a reflection of the wave, and we can listen to the echo of this electromagnetic wave coming from the ionosphere. And this is exactly how an ionosome works. So an ionosome is basically a radar, an HF radar, that is able to send HF wave in the ionosphere with scanning different frequency from 1 to 20 megahertz. So, and is able to listen to the echo coming from the ionosphere when a reflection happens. So we have these two antenna system, one that is transmitting the waves and one that is receiving the echo back. And by listen to this echo, we are able to infer the electron density of the ionosphere. But as we can see in details in few slides, the time between the sending of the wave and the listening of the echo back is related to the distance from the ground at which the electromagnetic wave was reflected. So we are able to, in some way, connect that particular frequency, so that particular electron density, to a distance, or a virtual distance, as we will see, from the ground. So this is, in a nutshell, how an ionosome works. This is an example of ionosomes. This is our ionosomes, so the one developed by INGV. The name is ICE, Advanced Ionospheric Sounder. On the left, you can see the electronics of the ionosomes, so all the stuff that is able to generate the electromagnetic wave and to listen to the echo, to the backscatter echo. And on the right, you can see the antennas. So the antennas in this case are mounted on a single mast with a 90 degrees angle each other. So one antenna, one delta antenna is able to transmit the waves, and one delta antenna is able to receive the wave. And here we have some peculiar parameters defining the technical details of the radar. So as we can see, the frequency range in which we are able to shoot the frequency is from 1 to 20 megahertz. The frequency resolution that is related to the height resolution with which we are able to sound the ionosphere is from 50 kilohertz to 100 kilohertz. So the resulting height resolution is 20 kilometers, more or less. And the minimum height at which we are able to sound the ionosphere is about 90 kilometers, and the maximum is 600 kilometers. So the sketch on the right, again, is showing that the ionosphere is a simple HF radar in which we have a transmitter and a receiver that is able to catch the backscatter waves and to measure the time between the transmission and of the waves and the listening of the echo back. So if we consider that an electromagnetic wave is passing through the ionosphere with a velocity equal to c, that is the light velocity, the speed of light in vacuum, but this is not, because we know that the refractive index is not equal to 1. But okay, let's assume for a moment that is true. We can define what we call the virtual height of the ionosphere, of that particular density in the ionosphere. So here you can see this simple equation defining related the virtual height of a particular electron density in the ionosphere and the time between the transmission and in which we transmit and receive the electromagnetic wave. So again, while passing through the ionosphere, the electromagnetic wave is feeling a refractive index that is not 1. So the virtual height is always greater than the real one. The results of the measure by an ionosome is what we call an ionogram. That is this sketch here at the bottom, and we can see that is basically a plot in which we have in the x-axis the frequency of the wave we are sending through the ionosphere, and in y-axis the virtual height of the echo received by the ionosphere. So here you can recognize some singularities in these traces. So this point, that are exactly the critical frequency of the ionospheric layer. So each of these points here is representing the critical frequency, and so the electron density of a particular layer of the ionosphere. So now here we can see that are two different traces, one in red and one in green, that are called usually ordinary and extraordinary trace. Do you know why? Some ideas on the chat? Okay, you are too shy. So the reason is the presence of the magnetic field. Do you remember? When a magnetic field is present, when a plasma is embedded in a magnetic field, you have that plus minus in the equation defining the refractive index. So basically, the two different polarization of the wave are feeling different refractive index. So the velocity with which they propagate in the ionosphere are different. So different are the time with which receive the echo back. And this results in two different traces in an ionogram. And as we probably see in the, I don't know if later on, but the distance between the ordinary and the extraordinary trace can give you a measure of the intensity of the magnetic field present in that point. So this is an indirect way to measure the intensity of the magnetic field. So let's go a little bit deeper in the study of the ionogram. As I already mentioned, the ionograms is able to give you the ionospheric characteristics. So the ionospheric parameter related to the altitude and density, electron density of the peak of the ionospheric layer. So here we can recognize the characteristic of the E layer, so the FOA critical frequency, and HAE, sorry, that is the altitude of the E layer. The same for the F1 layer in red here, and the same for the blue characteristic here that are related to the F2 layer. So when we look at an ionogram, we are basically looking at the distribution of the electron density on the ionosphere. And this is crucial for the study of the variation of the ionosphere, both the regular variation, but especially the variation induced by, for example, space weather events. So how an ionosome is usually used to monitor the ionosphere? Usually an ionosome is able to scan all the frequency from 1 to 20 megahertz, so to produce an ionogram every 5 minutes, 10 minutes, 15 minutes. It depends on the setup of that particular ionosome. But basically what we did is to monitor continuously the ionosphere by using an ionosome. So this way we can obtain, let's say, a time series of the characteristics of the ionosphere. In this image here, we are looking at, on the left, on the behavior of the FOF2 parameter, that is the critical frequency of the F2 layer, expressed in megahertz, from the ionosome we have installed in Rome, Italy, during an entire day. So here we can see the variation, the daily variation of the critical frequency, so the electron density of the F2 layer, that has, as expected, a peak at a local noon, that is here. And this is the green points. The yellow one represented 27 days median of this parameter. That is a kind of way we used to define a baseline, a quiet condition for the FOF2 layer. And 27 because this is the time of the sun rotation. So by calculating that 27 median, we have an idea about the baseline, about the quiet condition of that parameter. And as you can see here, basically in this particular day, nothing has happened. So the behavior of the measured FOF2 and the median FOF2 is quite similar. On the right plot, you have another representation of the FOF2, but this time you have in blue the 27 days median of the FOF2, in green again the measured parameter, and in yellow the validated parameter. Why? Because what we call measured FOF2 is actually a parameter that is derived from an ionogram. So we can derive the parameters of the ionosphere from an ionogram in two ways. By using an automatic scaling software, and there are 2 or 3 basically that the scientific community is using, and one of them it was developed at INGP. The name is Autoscala. Another very famous one is Artist, that was developed by the Massachusetts Institute, Lowell University in Massachusetts. That are basically software that are image recognition software, basically. So we are able to, with this software, to analyze the image, so the ionogram, and to infer automatically the characteristics of the ionograms, so the parameters of the ionosphere. But sometimes it happens that the software fails. So as in this case, here, you can see that the green points are not there for this period of time. because the software was not able to infer the parameter by looking at the ionograms because of the noise, because of the because something is going on in the ionosphere, and this is something that the software is not able to take into account. So for different reasons, but and this is why for let's say a deeper scientific understanding of the ionosphere, we need the human activity. So we need an operator, an expert operator that is able to look at the ionograms and infer the parameter by looking by human eyes to the ionogram. And this is the value we can obtain. We have here with this yellow cube. You can see that in most of the cases, the two measures are quite close, but sometimes the autoscaling software is failing and the operator, the human eyes, are needed. So now this is a little trick for you. I want to invite you to let me know if you can see the difference between these two ionograms. Okay, apart from the color of the traces for sure, but I mean, by looking at the shape of the traces of these two ionograms, do you see any difference in these two plots? No one?
Maybe you can help them. Okay. There are no peaks.
More or less. This is correct. Yeah. This is quite usual night side ionograms, and this is a day side ionogram. So here on the right plot, we can see, as Maria was saying, that we have different peaks here. So we have the E region, F1 region, F2 region, F2 peaks. So here we can recognize an electron density distribution that shows all the peaks of the ionosphere: E region, F1 region, F2 region. On the left plot, you have a typical night side ionograms, and as you maybe remember, during the night side, the E layer, D layer, and F1 layer tend to disappear. So the ionosphere is basically characterized by a Chapman layer that is describing the F region. So only one peak. It's not true, there is no peak in the left plot. There is one peak, that is this one, that represents the FOF2 critical frequency, so the peak of the F2 layer. Here you have the typical day side and night side profile, in which you can see during the night the F region, and during the day the DE, F1, and F2 region. In fact, here you can maybe read the time of this ionogram. That was 3:54, 3:55 during the night in Rome. And here you can see the parameter automatically scaled by the software we use there, so Autoscala software. And as you can see, the software was correctly able to catch the FOF2 critical frequency and not the other ones, because the other layers are not present at that time. Here, just to show you a typical example of the output of the automatic scaling software. So on the top plot, you have an ionogram recorded by the Ionosome in Rome, and the parameters in this table related to this ionogram. So virtual height and critical frequency of the peak of the ionospheric layer. And then on the bottom plot, you have, as you can see, different colored curves that are: the blue one is the reconstructed ordinary trace by the software. So the software is looking at the picture, is looking at the ionograms, and by using target function, but I don't want to go into details, is able to reconstruct the shape of the trace. So here you can see superimposed the blue one, that is the one reconstructed by the software, that is in this case not so reliable, and the white one, that is the one actually recorded by the ionosome. And in green, you can see the reconstructed vertical profile by the profiler included in the automatic scaling software. So we are able to reconstruct the trace of the ionogram, and by analyzing this trace, we are able to give a correspondence between the critical frequency on the ionograms and on the reconstructed trace and the electron density at a given height. And this is a quite complicated process, because if you remember, the height, the altitude we can get from the ionogram is a virtual one. It's not the real one. So the software is applying a quite complicated inverse problem in order to retrieve the real, let's say real or quasi-real altitude corresponding to a given electron density. So we are passing from the virtual height to the real height, physical height. And this is it for the HF sounding of the ionosphere. Any questions?
Okay, I would like just to add a comment to the last part of the explanation by Claudio. Say that we do need both the approach, the auto-scaling and the validation of the interpretation of the ionograms, because for space weather issue, we need to have real-time or quasi-real-time information on the condition of the ionosphere in order to be useful for the end users that are rely on that technology that can be affected by the ionosphere. While for the validation of the data, they are the ones that we need to study the ionosphere. So we need more reliable information on the ionosphere. As you have seen from the example that Claudio shown in the last slides, the autoscale is not always capable to catch the real information, the actual information. So for this reason, we need both the approach, space weather approach with the autoscaling that is capable to provide real or quasi-real, near real-time information, and the validation data, validated data for the study of the ionosphere. You have a couple of questions.
Okay, just for sake of curiosity, this is why we know that some Chinese institution has a lot of operators working 24/7 and scaling in quasi-real time ionogram by hand. This is crucial for space weather application, but this is something that is not so easy to realize.
So about the description of the Appleton-Hartree equation, Claudio, the question is the approximation of the refractive index always fulfilled in the ionosphere?
It depends on the approximation. Let's say that the approximation is are never realized in the ionosphere. I mean, the collision are always there, and that are important, crucial in the D layer, for example. So for the transmission of low frequency in the ionosphere, the approximation of the magnetic field equal to 0 is not valid, never, because the magnetic field is there. So the approximations are approximations. We are able to describe the ionosphere in this way because of this approximation. So they are quite reliable in most of the cases, but are not valid.
The table API is only available for Rome.
The table, you mean the one from the ionograms?
I think so.
No, it's okay. As we will see tomorrow, we have a database in which you can catch all the data we are producing. We have several ionosomes, one in Tucumán here, one in Bahia Blanca, again in Argentina, one in Rome, actually two in Rome, and one in Gibilmanna, southern of Italy. So for all these ionosomes, the parameters are available in quasi-real time, provided by Autoscala software, and are available on our database that we are going to show tomorrow.
And in the near future, also in Kenya.
Also in Kenya, yeah.
So
We have a project just started to install one of our ionosomes in the Broglio Space Center, the Italian Space Center in Malindi, Kenya.
How many times does it take to measure the data obtained on an ionogram?
Okay, it depends on the ionosome, but with the ICE ionosome, we are able to scan all the frequencies and to listen to all the echoes in a couple of minutes. So we measure a couple of minutes every 15 minutes, typically.
How would an ionogram look at the event of a solar flare?
Say it again.
How would an ionogram look at the event of a solar flare?
Okay. Yeah. Okay. I'm going to show something about the effects on the solar flare maybe tomorrow. But consider that a solar flare is a sudden event, electromagnetic wave that is able to induce an extra ionization in the ionosphere. So basically, what we can get on the ionograms is an enhancement of the critical frequency of the F2 layer in particular. So you can see a sudden increase on the F2 layer critical frequency.
Is there a reason to opt for an image processing approach to the analysis as opposed to raw data capture to do the fitting?
This is a very good question. Good. I mean, when I at the beginning of my PhD, I was trying to look at the ionograms in a different way. But I mean, if the ionogram is quite close to an ideal one, so you have no noise, no fake traces on the ionograms, no extra reflection, you can assume, okay, I have only one point for each frequency, each altitude. Okay. So if this is true, we have numbers that are related to different frequencies. So we have a one-to-one relation between the frequency and the altitude. But this is not true in most of the cases, because you have a lot of noise, you have different reflection, because an electromagnetic wave is mainly reflected when the frequency is equal to the frequency of the plasma frequency. But some energy could go higher. So basically what you have when you look at to a real ionogram is a lot of noise. And this is why an image recognition technique is very useful, because you are able in this way to cancel most of the noise on the ionogram. There are different techniques, but they are quite always related to image processing. Yeah, sure. Yeah.
Closer to the mic.
Okay. May I comment a little thing about the fact of this? My PhD was in fact on automatic detection using the ionograms and the raw data. So basically what we did is try to do automatic recognition of each layer, but also to clean the data, to clean the points. That's not an easy task.
No.
And we have some algorithm already published about that. But many of them, and there's not only this issue, but there are another issue with the instrumentation regarding the time of each sounding. So that's the main point. That's the main reason why we cannot put online these algorithms. So this is, I think this is the most. Now the new sounders may have this possibility.
Yeah,
but
yeah,
the
sure.
last one that already working is not able to perform this automatic algorithm.
No, it's true. I recently reviewed a paper by Chinese colleagues that in which they have shown a technique based on deep learning or something like this, as usual in the last year. So you have several approaches you can use for the automatic scaling of the software. But I mean, one method is to develop an algorithm that is more or less able to scale an ionogram as a prototype system. Another stuff is to put an algorithm online that is able and reliable to be online and to work continuously, giving reliable measurements. So this is the real gap.
Some of these algorithms
Sure.
work very good.
Yeah, otherwise the others
Sorry.
cannot hear.
Another important point is that most of these algorithms rely on the local and the local ionosphere.
Yeah.
So the timing of the algorithm is local, and we try to do it worldwide. So tuning that algorithms is very hard. So maybe if this is we know using this kind of autoscala is a good thing to work on real time. So locally, the problem is the local ionosphere.
Yeah, this is not by chance. We have shown ionograms from Rome. It is a mid-latitude, very mid-latitude station. Because at low latitude and the high latitude, as Lucilla was mentioning, there are several processes, several irregularities that occur, and these reflect on the ionogram. Just to give you an example, at low latitude, you have daily, what we call spread F condition. There is a spread of the trace around the F2 peak. So we are not able, and we are not anymore able to detect the exact frequency of the peak because we have this spread of the trace that is due to the presence of, let's say, small-scale irregularities in the electron density. So
Ryan is asking which direction of the sky is the Ionosome directed?
okay, the lobe of the antenna transmitting the wave is a kind of a cone like this.
In the vertical direction.
In the vertical direction, for sure. Okay, I'm going to say something. In the vertical direction with an angle of 30 degrees from the vertical to the limit of the cone of the lobe of the transmitting antenna, usually. So this is valid in the case of the vertical sounding. So in this case, we have the transmitting antenna and the receiving antenna that are located in the very same point. So we are shooting frequency on the vertical and we are listening to the echo coming back almost from the vertical. Okay, because the ionosphere is not a mirror. So some signal can come from slightly different direction. But we can do also a bistatic radar. So a transmitting antenna in one place and a receiving antenna thousands of kilometers away. So we are shooting frequency in this case in an oblique direction, and the frequency will be reflected by following basically the Snell law by the ionosphere as it's going down in the other direction. So we are able to transmit and receive the signal in another place. And this is how the HF radio communication works. Okay?
And a fluctuation, what magnitude in the FOF2 plot can be considered disturbances to which we must pay attention?
This is a very good question. It depends on the latitude, on the event we are considering. I mean, as usual, if you consider an anomaly, something that is far from the climatological behaviors, you can, for example, define a median of the parameter and a standard deviation, for example. So we can define a threshold in the standard deviation with which you can say, okay, if I have a measure that is above or below the median, plus or minus 2 standard deviation, 2 sigmas, 3 sigmas, or it depends on what you are, on what you want to read on the data. I mean, if you are looking to very small perturbation induced, for example, by an earthquake, a nuclear explosion, or something like this, you can consider very small deviation. If you are looking at the effect of a huge geomagnetic storm, you can have a very, very large deviation from the climatological behavior. So the answer is it depends.
And I would add also the question about the noise introduced by the measurements. So there are ionosomes. All the ionosomes are generally not more noisy than the modern ionosomes, and also the interpretation of the data introduce also other errors. So little deviation can be very well studied and very carefully cataloged as due to a space weather ionosphere. They can be due also to malfunctioning noisy errors in the scaling, the other things that are not due to the ionosphere.
Yes, this is why when we look at the parameters, we look not only at the magnitude of the deviation, but also on how long the deviation stands. So if you have a peak, spike on the data, you can say, okay, this is a measurements error, so I can discard this data. But if you have a quite, let's say, smooth behavior or a deviation that lasts for several ionograms, you can say, okay, this is feasible.
Yes, I would like to
Okay, yes, I will mention briefly again, the local process is also may have irregularities that may hide some space weather.
Yeah.
So this is, and in low latitude, I've seen a lot.
It's very frequent.
It's very frequent. So it's not that easy to do the backward relationship from one ionospheric irregularity to the space weather driver, let's say. So this is different when you are working with global parameters such as solar wind.
Yeah.
So the local ionosphere is very important.
The ionospheric weather is still a challenge.
This is why we are here, basically. Otherwise, we will be fired.
Yes, we have a job.
So yeah, this is true what Graciela was mentioning. This is particularly true when we are looking at, for example, the coupling between the lithosphere or lower atmosphere and the ionosphere. Because in this case, space weather events can completely hide the effects that are order of magnitude below the ones induced by the space weather, can completely hide the effect of the lithosphere atmosphere coupling into the ionosphere. No other question? So now it's time for a coffee break. A bit about the HF soundings of the ionosphere. That is, as I said, the very first instrument we used to measure the ionosphere since the 1940, something like this, so a lot of decades. But this is not the only one, and this is not nowadays the most, let's say, present in the world, because each ionosome costs a lot, from tens of thousands of euros up to hundreds of thousands of euros. So we have a quite distributed network of ionosomes. I don't know, between 100 and 200 ionosomes all over the world. But nowadays, the instruments that are more used to probe the ionosphere is the GNSS, so the GNSS receiver. What GNSS means? GNSS stands for Global Navigation Satellite Systems, and this is the name we gave to each of the system, each of the satellites constellation that are flying in order to provide a positioning system. The most famous one is the historically also the first one, the American GPS, that you already know, because each of us use GPS daily, every day, with the smartphone, with the car, with the GPS receiver are everywhere. But GPS is not the only one. We have the Russian GLONASS, the European Galileo, that is the youngest, and other constellation by the Chinese community, so Beidou and blah, blah, blah. So what GNSS are? We have several satellites constellation that is flying at what we call medium Earth orbit. So at about 20,000 kilometers from the Earth's surface. Medium Earth orbit because we have the low Earth orbit that is flying into the ionosphere, and that is useful as well to probe the ionosphere at about 400, 500, 600 kilometers, and the geostationary satellites that is flying at 36,000 kilometers. So the GNSS are in the middle. In this table, you can see some characteristics of the constellations, of the satellites, of the orbits of the satellite. And as you can see, all the constellations have quasi-polar orbit. So the inclination of the orbit is different for each constellation. For example, here you can see the GPS. The inclination of the orbit of the GPS is 55 degrees, 45 for GLONASS, 56 for Galileo, and so on and so forth. Different kind of satellites, but all the constellations have in common that are able to transmit signals at least 2 different frequencies in L-band, so between 1 and 2 gigahertz. And this is crucial for the ionospheric sounding. And this is crucial to, as we will see in a while, to correct the impact of the ionosphere on the positioning. So the fact that the signal that the GNSS constellation are transmitting are more than one is due to the presence of the ionosphere. So here we have a sketch in which I put all the frequency and on all the bandwidth of the signals transmitted by the GNSS constellation. In particular, the yellow one are the frequency transmitted by the GPS, and as you can see, GPS transmits nowadays 3 different frequencies that are L1 about 1.5 gigahertz, L2 about 1.2 gigahertz, and L5 that is below in frequency. So we have different frequencies, all in L-band, so all in frequency that are able to pass through the ionosphere. So this kind of frequency are not reflected by the ionosphere, because we want to receive the signal from the satellite that is flying above the ionosphere down to the ground surface by the receiver. So we need signals that are able to pass through the ionosphere, not to be reflected as in the case of HF signal. This signal has very long code embedded in the signal that is useful to recognize, to measure the time, the flight time of the signal from the satellite down to the ground, and is modulated in order to provide some navigational information. So information that the GNSS receiver can use to calculate the position of the satellite at a given time. And most important, again important, is the polarization of the signal. That is a circular polarization, because as we have seen before, the magnetic field is able to induce a splitting of the polarization, and the ionosphere, together with the magnetic field, is able to rotate the polarization of an electromagnetic wave. So the circular polarization is due to the fact that the circular polarization itself is not affected by the so-called Faraday rotation, that is the rotation induced by the ionosphere and the magnetic field together. So what a GNSS receiver is? A GNSS receiver is basically a clock. So what we measure with a GNSS receiver is basically a time, the time between the moment in which the signal leaves the satellites and the time in which the signal reaches the receiver. So every GNSS receiver has its own very precise clock, and the accuracy and precision of the clock determine the cost of the receiver, basically. So this is why you have few euros receivers and tens of thousands of euros receiver, GNSS receiver. So basically it's a clock that is able to measure the code embedded in the signal and the phase of the signal as received at ground. So what we are measuring here is the time, the flight time of the signal by means of code measurements, so the measurements of the code inside the signal, and carrier phase measurements, so the phase of the signal itself, and the Doppler measurement that we are not going to describe here. And due to the modulation of the navigational message on inside the signals of the GNSS receiver, the GNSS receiver is able to compute also the position of the satellites at each given time. So at the end, the receiver, by doing a triangulation, more or less, is able to determine its position, velocity, and time. So this is, in a nutshell, how a GNSS receiver works. So what happened to the signal when the signal traveled from the satellite down to the ground? The signal is affected by several contributions that are represented here. So here you have the P, that is the code measurements of the signal, and phi, that is the phase measurements of the signal. And as you can see here, you have a different contribution that are the geometrical part of the signal, so the distance, the physical distance between the satellite and the receiver, an error due to the clock offset of the receiver and the satellites, the error induced by the troposphere, especially by the water vapor in the troposphere, and the error induced by the ionosphere. That, as you can see from the sketch on the right, is one of the most impacting contribution to the propagation of the signal. And then, for what concerns the phase measurements, you have the so-called ambiguity of the phase measurements. So to understand what ambiguity is, you can imagine that you are handling a rope with several nodes at a certain distance each other, and you are feeling the nodes passing through your hands when the rope is running. So if at a certain point you lost the connection with the rope, and then after a certain period of time, you catch the rope again, you can feel the distance between two nodes that are close to each other, but you don't know how many nodes have passed through your hands during the time in which you lost the connection with the rope. So basically, this is just an example to give you an idea of what the phase ambiguity is. So when you catch a signal from a receiver, you are able to measure the fraction of the cycle of the phase of the signal. But you don't know how many cycles I mean, you had before you catch the signal. Okay, so since I mean, sometimes happen that the disturbances of the ionosphere induce a completely loss of lock of the signal. So when you catch again the signal, you have an ambiguity on the phase measurements that you are not able, in principle, to determine in a very accurate way. But there are several techniques in order to estimate this phase ambiguity. But this is very important because this is very impacting in the phase measurements of the GNSS signal. And then we have some hardware biases that is due basically to the noise induced by the electronics of the receiver and the satellites. So you can have different, let's say, response of the electronics to different frequency. So you can have a bias in the time you are measuring for different frequencies. And then other stochastic error induced by, for example, the multipath effects. So the reflection of the waves by buildings, by trees, by something that is surrounding the antenna of the GNSS receiver. But let's focus on the ionospheric contribution. If you look, if you pay attention to the ionospheric contribution, you can see that the sign of the contribution is the opposite in case of phase measurements and in case of code measurements. So basically what the ionosphere is doing is to induce a delay in the code measurements and a phase advance. So the velocity, the phase velocity of the measurements is higher than in the vacuum, and the group velocity of the signal is less than the speed of light in the vacuum. Okay, so you have a group delay and the phase advance. This is how the ionosphere is impacting the signal. Another important consideration is that most of these contributions are not dispersive, so are not depending on the frequency, but the ionospheric contribution do. So the ionospheric contribution is different for different frequencies, because we have seen that the refractive index of the ionosphere depends on the frequency of the electromagnetic wave that is passing through the ionosphere. And this is not for the tropospheric contribution, for example. The tropospheric contribution is not dispersive contribution, so it's equal for each frequency. Okay, and this is how we exploit the phase and code measurements on different frequencies to infer the ionospheric contribution from the GNSS signals. So now we know that we have measurements of the GNSS signals, code and phase, on different frequencies. So we can combine these measurements to obtain different kind of information. And we perform what we call linear combination of the signal. We have basically, okay, there are other, but the most important are two linear combinations that are named ionosphere free combination and geometry free combination. As the names are saying, the ionosphere free combination is a combination of the two frequencies measurements that is able to cancel out the ionospheric contribution from the signal, at least at the first order, and this is very important for what Lucilla is going to say in a while, and the geometry free combination. That is the combination we use to actually infer ionospheric electron content, ionospheric distribution of the electrons, that is able to cancel out the geometrical part of the signal traveling from the satellite to the receiver. Okay? So how we can exploit the GNSS measurements in order to infer information about the electron density into the ionosphere. Here we have the definition of the optical path that a signal is traveling when a signal is traveling from a satellite down to the receiver. So here we have the integral of the refractive index along the direction satellite receiver. And here we have the expression of the refractive index in case of very high frequency. With very high, I mean frequency that are much higher than the plasma frequency. And this is the case for the L-band frequency. Okay, so we can express the refractive index like this. And by performing this simple calculation, we can obtain the geometrical path that is here indicated with D, and the ionospheric, let's say, optical path. So the path induced by the ionosphere that is proportional to this slant TC. So slant total electron content in the ionosphere. That is the integral from the receiver to the satellite of the electron density in the ionosphere. So now we know that the ionospheric effects induced on the propagation of the signal is proportional to the integrated electron density distribution along the direction receiver to satellite. Okay, we used to express TC in TC units, that is 10 to 16 electron per meter square, and with the TC we measured the electron content in a cylinder that has a 1 meter square base, and the height, that is the distance between the receiver and the satellite. Okay, so this is the definition of the TC, and this is a very important parameter. So if we have measurements on two different frequencies, we can perform the geometry-free combination. So the L1 minus L2 combination of the frequencies. And here you can see that this is the contribution to the geometry-free combination. As you can see, the geometry path of the signal from the satellite to receiver is not there anymore, because we are performing the geometry-free combination. And the troposphere is not there anymore, because the tropospheric effects on L1 and L2 are equal. So we are canceling out the tropospheric effects. So what remains here is the ionospheric effects plus the bias induced by the satellite, the receiver and the satellite, the phase ambiguity in the two different frequencies, and the stochastic error due to multipath or something like that. So by putting the definition of the TC inside this equation, and by transforming this equation from wavelength to TC unit, basically, we are able to obtain this expression of the code measurements. Excuse me, the phase measurements, the geometry-free combination of the phase measurements of the GNSS signal. That is due to the slant TC, the bias receiver, bias satellite, the ambiguity combination on the arc, that is set of continuous measurements of the GNSS signal, and the stochastic error. So, not working. Okay, and we can do the same for the code measurements. The only difference is that the phase ambiguity is not there, because the code measurements are absolute measurements. So we have not the ambiguity on the code measurement. But experimentally, we can see that, empirically, we can see that the noise on the phase measurements is quite low with respect to the noise on the code measurement. So we have the phase measurements with a very low noise, but we have there the ambiguity. We have the code measurements that are absolute, but we have a very high noise in the code measurements. So are going to do, what we are going to do, to combine these two measurements. So we can calculate over a single arc of observation the difference between the cold and phase measurements, and then we can subtract this median difference to the phase measurements. So basically, this is a way to estimate the phase ambiguity on the phase measurement. So at the end, we will obtain something that is proportional to the TC, that has the contribution of the biases and a mean stochastic error induced by the multiple. And this is the basic equation we use to calculate TC from the GNSS measurements, and we use to calibrate TC from the GNSS measurements, because we have to estimate these three components here in order to have an estimation of the slant TC starting from the GNSS. This is how what the calibration technique is doing. So I don't have time to go into details of the calibration technique, and this is a pity, because this is something that is very close to my expertise. But just to let you know that several techniques are able to estimate more or less the biases on the GNSS signals, and for most of the cases, we use an approximation to estimate the TC, that is the so-called thin shell approximation. So we are assuming that the ionosphere is a very thin layer at a given altitude. Usually, we assume the altitude as more or less the altitude of the F2 peak. So we can put this thin shell layer at 350, 400 kilometers, more or less. So by assuming that, we can, let's say, associate the TC measurements to a given point that we call the ionospheric pierce point. That is the point, the intersection point between the direction of the receiver satellite and the thin shell ionosphere. So we associate the TC measurements, that is actually integrated measurements along this path, to a single point, that is the ionospheric pierce point. By doing this, we are able to verticalize the TC. So passing from the slant TC, so the TC calculated from the receiver to the satellite, to a TC that we can imagine as the total electron content on the vertical of the ionospheric pierce point. And we usually do it by applying a simple geometrical mapping function that is expressed here as a function of the Hertz radius, the ionospheric initial height, and the elevation angle of the observation of the satellite. Okay, so we are able to pass from slant TC that show a clear behavior due to the changing in the elevation of the satellite, because lower is the elevation, biggest is the part of the ionosphere that the signal is passing through. So the TC will be higher for low elevation and lower for high elevation. By applying this mapping function, we are able to pass from slant to vertical TC, so we are able to catch the real variation of the TC due to the variation of the electron density in the ionosphere. Okay? So how we use these TC measurements? Just to give you a drop into the ocean, just an example on how we can exploit the TC to do a kind of climatology of the ionosphere. This is a paper we published when I was a PhD student, and we use the station from the Rete Brasileira de Monitoramento Continuo, or something like this, in Brazil, so that is a very dense GNSS network. By looking at the TC data during the entire 2012, so during a solar maximum activity. What we get is something like this, that this is the climatological behavior of the mean TC on each of these beams that are 1 degrees by 1 degrees latitude longitude in the region of Sao Paulo. And here we are able to catch the difference on TC, so on the integrated electron density into the ionosphere, induced by the different seasons. The black line is the isoline depicting the 15 degrees south magnetic latitude. Okay, that is approximately the position, the expected position of the southern crest of the equatorial anomaly. But as you can see, during the season, the position of the crest is varying a lot. And this is due to the variation of the equatorial electrojet, so the electric field that induced the plasma drift, the plasma uplift. And so then we are able to catch the difference in magnitude of the DC in the different seasons. So this is just to give you an idea on how to use the DC to perform a kind of climatological study of the ionosphere at a low latitude. Questions? This was just to give you a very, let's say, basic idea on DC measurement. I spent 10 years in learning some stuff like this. Other colleagues spent an entire life in developing techniques in DC. So it's a huge topic that I'm trying to squeeze in 15 minutes. So. No questions?
No questions.
Too much questions?
Maybe.
So I leave the floor to Lucilla.
Nice, thank you. Okay, guys, I would like to let you know that maybe we will be some minutes in late with the closing of our today's scheduling. I hope it will be not a problem for you. Anyhow, the course is recorded, so you could have the chance to look after at the following slides in case you have to disconnect in a few minutes. So another very important characteristics of the monitoring of the ionosphere by means of GNSS receivers is the possibility to study the so-called ionospheric scintillations. Scintillations are called like this in association with the optical visualization of the blinking of the stars, so of the scintillation of the stars that we can perceive sometimes also with bare eyes. And in this case, we are talking about the scintillation happening into the ionosphere. They are defined as, you can read in this slide, as phase and amplitude sudden fluctuation of the trans-ionospheric electromagnetic wave that are transmitted by the satellite and are received at ground or from receiver that are on board LEO satellite, low Earth orbit satellites. Scintillation are essentially due to the existence of inhomogeneity in the distribution of the electron density into the ionosphere. Because, of course, in first approximation, we can think to the ionosphere as a thick layer like this, very homogeneous, in which the numbers of the electrons in the space are evenly distributed. Of course, the reality is not the case. So we have a very uneven distribution of the electrons distribution, and this causes the effect of scintillation. But scintillation is index with respect to the passing through the ionosphere. So, in particular, this scintillation that again in this slide is repeated, that can be defined as sudden rapid fluctuation on both phase and amplitude of the received signal, GNSS signal, is an effect, and it is due to the presence of what we call the ionospheric plasma irregularities. The ionospheric plasma irregularities can be thought as a region in which the ionosphere presents a different electron density with respect to the ambient ionosphere. You can imagine, for instance, islands of high electron density concentration surrounded by a lower electron density concentration, or the opposite. You can think about, for instance, to region in which the electron density is very low with respect to the surrounding area. These are called, with a general name, ionospheric plasma irregularities. And scintillation are the effect of the diffraction of the signal that pass through the ionospheric plasma irregularities. When a signal passes from the transmitter on board a satellite, it's received at ground, and pass through a region of the ionosphere that presents ionospheric plasma irregularities, this signal can scintillate. So what you see is that is an example is given in this plot here, in which you have an enhancement of the noise of the signal. In this case, this is the phase of the signal. That's evident, that highlights the presence of some kind of irregularities along the path traveled by the signal to arrive to the receiver. How to monitor the scintillation occurrence? The standard way, so is a way that the scientists all over the world have decided to adopt as a common mode to observe and also to measure, quantify the intensity of the scintillation, is given by these two indices. One is called the sigma phi, and the other is called the S4. These are related to the scintillation on the phase of the received signal, the sigma phi, and on the amplitude of the received signal, and its name is S4. As you can see, they are both derived from the phase of the signal received at ground, and from the amplitude, from the intensity of the signal received from the GNSS receiver. But which kind of receivers we use? Here you are seeing three generations of receiver. The GSB 404 that was manufactured by the Novatel company. Then the Polar XS and the Polar X5S manufactured by Septentrio receiver, both of them. The Novatel receiver was formerly installed here since a few days ago in Tucumán, and then now we have replaced this old receiver with a new one, with a Polar X5S receiver by Septentrio. There are big difference among the two because first of all, the GSB was capable to catch to receive only GPS signals, while Polar X5S receiver is capable to track not only GPS but Galileo, GLONASS, Beidou, and geostationary L-band receivers. So you understand the number of information that is capable to record is widely amplified, and of course also the signal to noise ratio is better in the newest generation. These kind of receiver are capable to track the signal transmitted by the GNSS constellations at a very high rate. And we need this kind of high rate, in particular, in this case, we are talking about 50 Hz sampling frequency. So every 20 milliseconds, you have the record of the signal. We do need to have this high rate sampling frequency because the scintillation effects are very transient, are very fast effects. So we need to integrate to compute the integration on a certain time interval that generally is very fast, of a few seconds or 1 minute. And we do need to have in this time interval several measurements, several sampling of the signal in order to have a proper information. The navigational parameters, of course, are also stored. We do need again to deploy this scintillation receiver in a proper way. So the antenna has to be installed in a free or almost free field of view above and around in order to minimize as much as possible the multipath. And this kind of receiver have a firmware embedded. This firmware is capable to compute in near real time the scintillation indices that we need to use for space weather applications. So a deeper look in what is a scintillation. First of all, the amplitude scintillation is caused, because there's an effect, is caused essentially by one mechanism, the diffraction. The diffraction is triggered by small scale irregularities. And what is small when we talk about GNSS signals, you can see in the top right of this slide, in which you have an assessment of the first Fresnel zone. But let's go back for a while. In this ideal plot, of course, it's not a real plot, and it's an ideal sketch. You see in logarithmic scale the power spectrum density of the intensity of the signal received at ground, of course, as function of the frequency, in which you see the typical shape of the intensity of the signal received at ground when you have scintillation. So with these two lines, two different slope, one is almost horizontal. In this sketch, is a simplified sketch, is horizontal, and here you have a different behavior that's in which you see a certain slope of the red line. The border between the two behavior is identified as the Fresnel frequency. That's maybe you remember from the optical theory, defined and turn also the first Fresnel zone, that is the dimension that you need when you would like to observe a diffraction due to the encountering of the electromagnetic wave with this obstacle of a certain dimension. So if we do a very rough estimate of the Fresnel zone from the GNSS signal, you can see that we can derive this information looking at the relative velocity of the ray path with respect to the ionosphere, And we know in advance the wavelength of the electromagnetic wave, because in this case is the one of the first carrier frequency, the L1, that is around 19 centimeter. Again, as Claudio did in the previous computation of the TC verticalization, we assume that the ionosphere is mainly concentrated around the maximum of the electron density, so around the F2 peak that we can fix at 350 kilometers. If you do this simple computation, you derive this dimension for the Fresnel frequency that is about 250 meters. So when we talk about small scale, this is the upper boundary. We mean that the dimension of the irregularities, remember the horizontal dimension, the dimension of the irregularity that can cause scintillation on the GNSS signal received ground is for irregularities of dimension up to 250 meters. So this is what we define as small scale, looking at the wavelength of L1, of L-band, generally speaking. Of course, if we use other kind of probing, other wavelengths, for instance, VHF, UHF spectrum, this dimension is greater. So the plethora, the variety of scales is greater, because we arrive to around 1 kilometer scale. So the irregularities that can induce scintillation on VHF or UHF signals are for irregularities of dimension up to 1 kilometer in that case. So you have more kind of irregularities, different dimension of irregularities with respect to the GNSS probing. So let's go back to this mechanism. So diffraction triggered by scales of irregularities up to hundreds of meters, we can say, as order of magnitude. This is a stochastic effect. The stochastic effect is usual, the actual problem for GNSS positioning, because it's an effect that is hardly predictable and that it comes very suddenly. So this is the main issue for space weather, the stochastic effect. What is the phase scintillation? The phase scintillation index accounts for two mechanisms. The diffraction, the one that we have just seen in the previous slides. So the one, I repeat, that is due to the presence in the ray path of irregularities of dimension up to hundreds of meters. But there is also, on the phase scintillation index, there is also the contribution of refraction. Refraction is due to the whole scale range that scale with 1 over f. In particular, we care about the fact that the phase scintillation, as truly assessed, is the phase scintillation to the stochastic contribution, so to the diffraction, to the presence of small scale irregularities. Then we can have a deterministic effect that is superimposed on the stochastic effect that we called not phase scintillation, but phase fluctuation. This contribution, the phase fluctuation, can be well estimated through the ionospheric free linear combination. What Claudio already mentioned in his description of the TC derivation, because essentially for what concerns scintillation, we care we are interested in isolating the secondary and third and the order greater than the first one in the study in the approximation of the ionosphere. So the definition of the phase scintillation we can define as the residual after destruction of the structure, very difficult to say, extraction of the structure, that follow the 1/f frequency dependence. And the best estimators is the ionospheric prelinear combination. The phase scintillation is dependent on the frequency content and has to be derived after the trending of the phase that is received ground. The trending is needed because essentially there is a relative movement between the satellite and the ionosphere. So we have to take into account this shifting, and the phase has to be detrended. But how to detrend the phase? Let's go back to the power spectrum density of the phase in blue in this sketch, and in red of the amplitude of the signal. When we found with the amplitude of the signal the Fresnel frequency, we have found the best frequency cutoff that we can choose for the trending the phase. The nominal frequency that the receivers that I have just described as the September receiver that we installed a few days ago here in Tucumán, the definition, the nominal standard computation of the phase index by the firmware of this kind of receiver is 0.1 Hertz. But as you can see in this sketch, not always 0.1 Hertz is the right choice, as in this case. And for sure is not the right choice at high latitudes, where the ionosphere move very fast with respect to low or middle latitudes. And so in that case, the choice of 0.1 Hertz as a cutoff frequency to detrend the phase of the signal is not the right choice to remove all the deterministic contribution. So all the part that we call phase fluctuation that is not phase scintillation, but is due to essentially fluctuation on the TC. So generally, what happens if we use in a blind approach the sigma phi estimated by the firmware with a 0.1 Hertz cutoff frequency, is that we have an overestimation of the sigma phi. So how look like the real spectrum? This is an example from Svalbard Island in 2007, November 2007, as you can see from the top label. Svalbard Islands are very close to the North Pole, north of Norway. You can see, you can recognize the two behavior that we have seen in the previous sketch. Sorry, in which you have the phase as a curve that can be roughly fitted by a straight line with only one slope, while for the amplitude you have these two behavior with almost horizontal behavior on the power spectral density, and then a slope of a certain angular coefficient. These are the phase and the amplitude of the signal as seen by the power spectral density from a real signal. where they happen, the scintillations. In principle, they can occur everywhere in the ionosphere, because, as I have said, the cause are the existence of irregularities in the distribution of the electron density. But they are more frequent to occur at very high latitude, so from auroral to cusp to polar latitudes, and around the magnetic equator, for the existence of what we have seen as defined the equatorial ionospheric anomaly, with this two big crests. Let me see. Where is the arrow? Okay. These are the two crests of the equatorial anomaly. These are the high latitude regions. As you can see, this is the noise induced by the presence of small-scale irregularities on L band. And this is for the solar maximum, and this is for the solar minimum. Again, we are coming back to a climatological representation. This is an average representation, a very famous paper of 2002. But anyhow, also during minimum, you see that the regions that are more affected by scintillation are always the same. So, time for questions.
Yeah, we have one. How can we measure the impact on the time transmission on the GNSS signals coming from the troposphere? This is a very good question. We have several techniques to measure. I mean, usually we are interested in the opposite. So by using the delay on the GNSS signal transmission, we want to know which is the how much water vapor you have in the troposphere. So this is usually the problem you are facing. So basically, you have these GNSS signals, you know the time transmission delay, and you can model by starting from this delay the so-called zenithal water delay or something like this. I cannot remember now the name exactly. That is related to the water vapor contained in included in the troposphere.
Zenithal tropospheric delay,
ZTD. Tropospheric delay. Yeah, exactly. So this is more or less what, but this is not done by using a linear combination. So if you combine the two frequencies, you are canceling out the tropospheric emission. If you want to do the opposite, I mean, you want to estimate the GNSS signal delay, you need, for example, a radio soundings that is able to give you the temperature and the humidity profile, vertical profile. So starting from the information on temperature and water vapor, you can estimate the GNSS signal delay. Another question is the Novatel receiver is obsolete.
Yes, we can say that now is a little bit obsolete, but it's still working very, very well. So in some cases, when you don't have any other option, it can be a good way to monitor the ionosphere. The question is that now, of course, the new generation are more reliable, and above all, they are capable to catch more constellations. But the Novatel receiver is still a very good tool to monitor the ionospheric scintillations.
No other question.
No other question. So we can go to the last slides. So we decide for the end of this day to go back to the climatology definition that we introduced at the very beginning on Tuesday, and to introduce what is the climatology of ionospheric scintillations. That is something that was not in place as a concept before our contribution. So we are quite proud from NGV to say that we were the first to publish a way, a technique to assess a climatology of the scintillation. And in this sense, in this framework, we meant to assess the general recurrent feature of the ionospheric irregularities dynamics and temporal evolution along data series, because climate is made on longer data series. Try to catch eventual correspondence with scintillation occurrence, looking at the studying the signal propagation to look for climatology of the irregularities distribution and evolution. We have made use of this technique, a totally empirical technique that is called ground-based scintillation climatology. This is a very simple block diagram to explain how it works. The scintillation climatology provides two kinds of products, so we can say. The map of occurrence of certain quantities and the map of mean of certain quantities. The occurrence map are the map, of course, of the occurrence of scintillation indices above a given threshold. So we have defined in advance a threshold above such threshold. We define what is scintillation, and below that threshold we define what is background noise. And for the mean, we in the root mean square values, we define not only the ionospheric condition given by the amplitude and phase scintillation indices, the vertical TC, the slant TC, and the rate of TC that we didn't have the time to define, but is the variance, the change, the temporal change of TC for physics studies. But we care also about the assessment of the receiver behavior, the receiver performance in that particular location, looking at the signal-to-noise ratio on the two carrier frequency and the code carrier standard deviation. In this table are summarized the main feature of how the scintillation climatology works. So we define, first of all, elevation angle threshold to try to minimize the multipath, so the scattering coming from obstacle surrounding the antenna. Then we adopt the verticalization of the scintillation indices to minimize the impact of the geometry in our assessment, a statistical accuracy. And again, we have fixed this value for the statistical accuracy, defined as this one. And then what are the output? So the map, for instance, the map of occurrence of scintillation indices are sorted according to geomagnetic condition. We can use whatever indices we want, the KP, DST, AE, whatever, or according also to the planetary magnetic field condition. For instance, VZ, negative or positive, open magnetosphere, closed magnetosphere, and so on. So a couple of examples how multipath can jeopardize the data quality. We have to be very careful when we read a map of S4 mean, for instance, on L1, L2, as in this case. What we are seeing is the mean of S4 over a long period of time. plotted in function of the elevation and of the azimuth with respect to the antenna, of course. And the color is the intensity of the scintillation indices. So at first glance, we can say that these are the region on LL1, and these are the region on L2 in which the scintillation indices is appearing higher. But if we cut the elevation angle at 20 degrees, we see that most of these enhancement are eliminated, are deleted by our map, simply because in that case we were luckily seen at multipath, not at ionospheric contribution. So we have to be very careful when we interpret the scintillation mapping. This is a characterization according to KP levels of the scintillation on the face of the signal. This is a plot of magnetic latitude, magnetic local time reference, quiet days for KP lower than 3, and disturbed days from 4 to 9 for KP. And these gray and red curves identify the boundary of the auroral oval. You see the cusp, the region towards the sun, and the tail of the magnetosphere in these two regions. And you can perceive how during disturbed periods you have an evident, significant enhancement on the occurrence of sigma phi, especially in the tail at the cusp. That is quite expected because we expect the recognition happening from the magnetopause at the nose, so in the sunward direction, or at the tail, so in this in the midnight, around midnight, from a magnetic point of view. So, in which way a climatology of scintillation can support the space weather? Essentially to provide a background. A good background derived from an empirical assessment with which we can compare the weather conditions. So if we are dealing with a particular storm, a certain storm, studying that storm with respect to a background, we can identify what can be generally detected as anomalies, as differences, discrepancies with respect to the general behavior. To do that, we do need a very long time series, and there are some papers here that maybe we can also update that we provide for your reading if you are interested. So, questions?
Thanks. See you tomorrow.
Okay.
So I guess we can
close.
session.
Okay. Thank you for your attendance, and we will see tomorrow for a recap and some space weather exercise.
Hasta mañana.
Hasta mañana.